Sir. Yes, sir. Yes, sir. Yes, sir. Yes, sir. Okay. I'll share my PPT, sir. One second. Sir, can you, the screen is visible, sir? My volume is fine, sir. Is it audible? Okay, sir. Thank you, Vijay, sir, for introduction. And I am L. Bhaskara from VIT Chennai, working in School of Mechanical Engineering. And before I start, I will thank organizing committee for giving me this opportunity. And in the today's talk, I'll give just brief introduction to finite element analysis, and I'll explain one case study where we are working currently in this project. We have completed one part of the study, and we are doing the second part of the study. That case study I'll explain. And this is mostly scientific, mostly R&D kind of project, but it is very very interesting project, so that you can also try in this area. And I think this is I think maybe third day of the course, mostly third day. Yeah. Okay, sir. Mostly, I think previous speakers you might have talked about the introduction part, but I'll spend few minutes on introduction part. Then I will move on to the case study. Before we start this introduction part, generally the scientific problems or any basic engineering problems, there are two kind of things. One is problems comes under simple geometry, simple boundary conditions, and material is simply isotopic material. There's one category. The other category, the problems of the second category comes under geometry is very complicated, and also boundary conditions are complex boundary conditions, and the material is not only isotropic material, and we have orthotropic material and anisotropic material, okay, and functionally created material and nano material, all these things. So in second category, and solving problem is not simple and straightforward. Whereas in first category, where geometry is very simple and you have very simple cases, like you have a simple uniform cross section and having simple loading conditions. Okay, so these kind of problems you can solve very easily. This let's say some load is acting, the area is uniform cross section. Therefore, if you want to find out deflection of this number here, I can find out directly by using basic elementary strength of materials or formulas. So I can find out delta equal to WL by AE. It is simple and straightforward. Okay. Whereas same problem, if it is like this, same thing, you are not changing. You have a load at the end, but there is a hole here. There is a hole you are providing here. There is a notch here. There is a notch here. So then this geometry becomes complicated. Why? Because you are providing two holes in the material and also notch is there. The reason providing this is essential. As per the application requirement, I need to provide this. So in this case, I need to do the analysis, right? I need to find out what is the deflection, what is the stress induced, all things I need to find out. So this I cannot find like first case using formula directly because of complicated geometry, right? With respect to geometry, I'm talking about. Therefore, in this case, you need another approach to solve these kind of problems. So there is a gap between the first and second. So this gap led to the development of several other techniques called numerical computational schemes, which includes finite difference method, finite element, and the boundary element method. And each method has got its own advantage and drawbacks. Okay. So the first case, what you are talking about is called closed form solutions. Closed form solution. That means what? They yields 100% accurate result. Okay, the first one. First case, what you are finding. In the second case, where finite difference method, finite element method, boundary element method, this method, when you are trying to solve these kind of problems, and they may not yield 100%. Maybe your results may be, I can say 98% accurate, or I can say 95% accurate, or 93% accurate. So, because these are approximate methods, these are approximate. Therefore, approximate methods always we are going to get only approximate results. Therefore, in approximate results, again, the best approximation you have to make always. How do you make best approximation? That we'll discuss just after a couple of minutes. And basically, this finite element analysis used to solve all domain of problems, maybe solid mechanics, fluid mechanics, heat transfer, okay, and other domains. So, for any problem, the basic idea is how to solve the basic equation, differential equations. You are going to solve the differential equations. Okay, and before we proceed, we should know why this finite element analysis is required. What is the need to use this? Okay, if you look at one simple example, I think this example we should know so that we can have better idea about how we are going to use these kind of problems. And if you look at this, only one case I'm going to show you why this is required. Let us say you have a function. Okay. So it's all about solving functions. Okay. How effectively you're going to solve the functions. The solving function is very simple if the function is very simple and involving very minimum number of terms. Same function, if it's complicated, it's very difficult to do the integration. So in this regard only, we are going to talk about two terms. One is exact way, other one is approximate way. These two approaches. Let us say in one case, you have a simple function. I have function fx. So this function is very simple case. Fx equal to c is very clearly defined and simple function 1 and 2. And let us say this is x1 and this point is x2. What I want to do is I want to find out area under this curve. That is a simple thing. Area I like to find out. So how to find out area under this? This I can find out easily by using integrating this. So area I can find out from this. Integrate this. What you have to integrate? The function you have to integrate between limits x1 to x2. This I can do easily. Fx equal to c dx integral c is constant, take it outside, integral dx, limits are x1 to x2, then this is nothing but x2 minus x1. Therefore here area is c into x2 minus x1. This is what you have computed area. I'm talking about simple thing. So this area is, I can say, 100% accurate. There is no 100% accurate. Now, in another case where you need to think differently. So this is, I have a second scenario like this. So I have, this is y and this is x. So I have a function like this. I have a function like this. 1, 2. Let us say this is x1 and let us say this is x2. How to find out area under this curve? This is where we need to think differently, because this function fx is not simple. Even though the function is simple, you cannot do the integration of this because the function is complicated. So how we are going to find the area under this? So what you have to do in this case, we don't have any direct approach because function is complicated. So what you can do is you can segment, you can divide this curve into small slices, small slices. For example, I am dividing this into slice 1, slice 2, slice 3, and so on, n slice. So this is a slice 1, 2, and so on, Sn. Now what I'm going to do is take first slice, this one, take first one, then find out the area, move on to the second one, find out the area. Therefore, in the second case, what you're going to do is you are going to find out total area is nothing but you are finding a1 plus a2 and so on an. Now, how to find out first area? When you're finding first area, the first slice I'm talking about, the first slice, if you draw to the larger scale, this is our first slice, and you're having the, this is what, just I'm drawing the analogic curve. This is slice 1. So let us say this is delta x, and let us say this point is y1, let us say this point is y2. So what I want to do is I want to find out area of this slice. So I can find out different approaches. Approach 1, what I'll do is here I'll draw horizontal line. I'll say this is A, B, C, D, E. So I'll assume this as a rectangle A, B, D, E, and I'll find out the area. I'm ignoring B, D, C, but I'm drawing larger scale, but actually it is not large, very small. Therefore, I'll assume this as a rectangle and I'll find out the area. This area is nothing but y1 into delta x. So in this way, your error is coming, how much it is? B, D, C. This you are leaving, this area you are leaving. So this area of the first one is not correct because error is there. This you are ignoring. This is approach 1. What I want to do is, this error is large, I want to minimize that error. So what you can do in approach 2, Instead of assuming this as a rectangle, assume this as a trapezoid. So draw a line like this. Now you are finding area like this. What is the area now? Area will be trapezoidal area y1 plus y2 by 2 into delta x. Okay. So A, B, C, D, E. Still this zone is there, right? This zone still there is a something you left over. So here also you are going to have an error. Here also there error is there. So what I have to do is still I have to minimize this error. Again in approach 3, what I have to do is try to assume that instead of linear, you assume some quadratic kind of thing. So I am assuming here quadratic curve. So B to C, I am going to join like this. So this is quadratic. So in third approach, error you are minimizing still. Still there is a gap, you see, after this black and top line, still there is small area is there. So still you left something. So there is an error. Again, what you have to try another approach 4. There, what I am doing, I am assuming cubic curve. I am assuming cubic curve. So cubic curve, if you draw, your line will be like this. So your increasing line like this. This is cubic. So what you are doing, you are assuming constant to linear, linear to quadratic, quadratic to again cubic. So you are increasing the order, hence the error you are minimizing. The error value you are minimizing. So here what you are doing, you are trying to estimate area 1 like this. Similarly, you are going to do area 2 and you are adding all the areas. Finally, whatever total area it is coming, it is not 100%. It is not 100% because of this reason. So it may be 98% or 97% depending on what kind of function you are assuming. So this is how you need to find out this. Basically, what you're going to do is when you're going to solve these kind of problems, always the solution is approximate. The solution is always approximate, not 100% accurate. So these differential equations you are going to solve. For solving any differential equations, we have 2 methods are available. One is exact solution, other one is approximate solution. What is exact solution? What is approximate solution? As I told already, exact solution here, you are going to get your solution 100% accurate. But the problem is, this is possible unless the problem is simple, the boundary is simple, loading is simple, then you can go for exact solutions. But if the geometry is complicated, lot of things are there, you cannot solve by using exact, then you have to move on to approximate solutions. In approximate solutions also, we have 2 methods. The first one is analytical solutions. In analytical solution, what you are going to have, we are going to get some formulas as solution. So here you are going to get equations as a solutions. Then in these equations, you may come up with some constants also. For example, when you are designing riveted joint and you are going to have some constant into root t, 6 root t. So diameter equal to 6 root t. This is what unmeans formula. So here look at this. What is 6 here? The 6 is, it is a how you got the 6 value. This is empirical value. How you got? There is no mathematical evidence for this equation. Similarly, when you design the board, you have some constants. Formula only, it involves constants for which mathematical evidence is not there. These are developed by conducting series of experiments, then finally arrive at this value 6. Okay, so in analytical solution, we are end up with some formulas based. And another one is numerical solutions. In numerical solutions, we are going to get numerical values for unknowns for domain. Always it gives some numbers, where the finite element analysis of finite element method is basically it is a numerical solutions. Numerical solutions, it is a FEA is a highly mathematical incentive. Okay. So a lot of equations are involved. we are going to solve equations by using the finite element analysis. Okay, so in that you have a systematic approach. What we are going to do is the finite element analysis. We are going to divide a given domain into a small slices. Let us call small pieces, subdomains. They are called as elements. Let us see here. This is what dividing into n number of parts. Now see here. There are two things here. This is called nodes. 1, 2, 3, 4, 5, 10. These are called nodes, and 4 and 5 connecting two nodes 4 and 5 is called as element. So we are discretizing this into nodes and elements, and this is what we call it as finite element. The shape here it is triangular element. Also we have a rectangular element. Okay, so nodes and elements, we are discretizing a given structure. That's what we are going to do, and this is what generalized process, discretizing the given structure. For doing this, we have different approaches. At the same time, we have a certain procedures are there, standard rules and regulations. You need to follow that when you are discretizing these kind of structures. Wherever it is possible, symmetry things, no need to do entire thing. Let us say this is a plate. For this plate, what we can do, I can take 1/4 of this. Then do the symmetry about this line and this line. We are going to study for the entire thing. By following this symmetric things, what we can do, we're getting two advantages. One is your computational time is very minimized. Second thing is your resources you can save. No need to store the entire thing. Right? So this is what advantage you should take whenever symmetry identified in a given geometry. And also some important precautions when you're doing discretization. This is very important. When you discretization, there are the points you need to remember. For example, there are two materials in our system, material 1 and material 2. So at the transition 1 to 2, you must identify a node. So here nodes, these along this line, nodes identified because at the interface, this is wherever there is interface, you must identify this is a node. Okay, at the bottom, this is a node. And also when the distributed load is acting, let us say here, exactly it has to start from this node and ends with at this node. But don't make it, a part of the element is subjected to loading starting and ending also at the part of the last element. This you need to avoid. Start from the one node and ends at the another node. Like that, you need to identify the nodes. And also, when you're identifying the nodes, one important thing is you, depending on the geometry, you need to give the node points. For example, here there is a geometry here that the load is acting. You can discretize this in simple way. I can make this as node 1 and this is node 2. And in between is not required because it is a uniform geometry. Same problem if something is load is acting here. Let us say some load is acting here. Then when you're discretizing this structure here, node 1, give the node at this point where load is acting, and this is node 3. Also, wherever there is a change in geometry, for example, here this is material 1 and this is material 2. There are two materials. So when you're giving this nodes, make it 1 and this is 2 and this is 3. Because 1 to 2 geometry is uniform, but 2 to 3 there is a sudden change in geometry. So there you need to give a one node. At the end there is another node. So like that, there are certain guidelines out there. You should take care when you are giving them. And also, wherever there is a boundary, you must give the node. Let us say here this is a boundary, there should be a node defined here. This is a boundary, you should define the nodes across this. So these important things you need to remember when you are giving node number and okay, and you need to give node wherever it is necessary as per these guidelines. And also there is another thing is called interpolation function. What is interpolation function? In FEA, what you are going to do, as you have discussed, you are defining nodes, two nodes, then there only you are finding the solution here. Let us say one problem is there, and here you are taking node 1, this is node 2, you are finding nodal displacements at 1 and 2. I know displacement at 1 and 2, but I want to find out displacement at this point. How to find out this? I need to find out displacement at this point. How to find out this? So what you are doing here, knowing nodal displacement at nodes 1 and 2, you can find out displacement. You can find out displacement at any point using the interpolation function. It is also called a shape function or approximate functions. These functions are very, very important and very useful in finite element analysis. What kind of shape function you have to choose, and how to choose the order. Is one-dimensional, two-dimensional, and 3D, and the selection of shape function is very, very important, because if you don't select proper shape function, then you cannot make a better approximation at a required point as per the. So this is what the shape function, and using shape function, we are able to find out field variable wherever you require other than your nodes you have defined. Similarly, I have taken this element here. It's a 1, 2, 3. I know the nodal displacements at 1, 2, 3. Let us say I want to find out value here, somewhere here. So what you can do, using shape functions, I can find out the field variable at this point. Let us say u, which is equal to n1 u1 plus n2 u2 plus n3 u3. So knowing field variable at the nodes, I can find out field variable at any point other than the nodes. This is what the shape function we are going to do. And the selection of shape function, it depends on what kind of things you are going to see there. Okay, it is 1D, 2D, and the order of the shape function is going to increase. So when the order is increases, then the accuracy is going to increase. That you will see that. And this is what the for one-dimensional things, you can assume the shape function like this: ux equal to a1 plus or alpha 1 plus alpha 2x. Order of x is 1, and for another shape function, you can take alpha 1 plus alpha 2x plus alpha 3x square. First one is 2-noded, third one is 3-noded. So from 1 to 2, what we can observe here is accuracy is going to increase. That observation you can do that. Remember, if the problem is simple, even if I take first one, 2-node and 3-node, both cases you are going to get the same result, because problem is simple. Okay, if this problem is somewhat complicated, then from 1 to 2, you can identify there is an improvement in the accuracy of the solution, or you can say error is going to reduce. And for two-dimensional regular elements, this is how we are going to take the shape functions: alpha 1 plus alpha 2x plus alpha 3y plus alpha 4xy, and v of like this you can take. For this, you can follow this Pascal triangle for 2D problems. Okay, see the constant: linear, quadratic, cubic. And one thing in case of area, I told you clearly. And when you're finding this, this is what you got, right? That first slice. So what you're doing, first you're taking constant. This much is error. Then I've tried linear. So let us say this is constant, 1 I'm saying, so 1 I'm taking. Still error is more. So in second case, I've taken linear. This is second, this is linear. Then what I've done, I've tried quadratic. So quadratic means what? I'm taking curve like this. This is quadratic. Let us say this is third. So then still there is a leftover thing is here. This is a leftover thing. There is an error. So what I've tried, cubic I've tried. So I'm going this. This is fourth one. Still something is left over. You tried last one. Try this. So this is 5. What you are doing when you are moving from 1 to 2, 2 to 3, 3 to 4, 4 to 5, order you are increasing. When you are increasing order, you are moving towards accurate result, or you can say error you are making tends to 0. Okay. So these are the essential things you should know that. Okay. And these all derivations we are not going to see because already you might have gone through all these things. And this is how we are going to do the discretization. This is what the elements. For one dimensional element, line element, rods, beams, trusses, frames, you can take this. This is node 1, node 2, 2 degree of freedom. For two-dimensional elements like triangular, quadrilateral, plate, shell, 2D, contina, we can take these elements. For 3D, we can take tetrahedral, rectangular prism, for 3D contina. For these elements, you need to select based on the type of problem you are going to solve. And this is what the discretization. For 1D, how we are going to discretize, and for 2D and for 3D. And when discretization also, there are some techniques you need to use. Those techniques also very important because when you are doing meshing, a few things you should know that wherever there is a critical sections are there, there your meshing should be fine and accurate. For example, you have a hole like this. So wherever there is a hole, as you know that there is a stress concentration exists here. Same problem here, right side I am showing here. There is the same problem here. When you apply the load here, then the flow of the stress lines, if I draw, the flow of the stress lines are moving like this. They're parallel to each other. See here, flow lines are how they're parallel, very smooth from one end to another under the load. Same thing, the right side, if I provide a hole for the same geometry, if I try to draw the flow of the stress lines, they are going to move like this. It's coming up to here. Suddenly there is a and coming here. Similar here, because of hole, suddenly there is a diversion and going like this. This is how the flow of the stress lines. So what is happening here? So at this level, here the stress is nominal stress. Very close to the hole, here, if you find out the stress is maximum, it is called stress riser. So there is a ratio of maximum stress to nominal stress is there here in this case. That means what? Wherever there is a hole and there is a stress riser, but that you can't avoid it because you need to provide a hole due to some other reason. So having hole is very essential, you need to have, but you should know that when you do the finite element analysis, very close to the hole, you try to use the mesh, very fine mesh, very refined mesh, very close to the hole. And this area, left side and the right side, that area meshing is up to normalness. But critical sections, you take very fine mesh. Okay, that you can see clearly when you are doing the. And this is a basic equation. You know that this is what finite element equation. And the K is a stiffness matrix. U is a nodal displacement vector. F is a nodal force vector. This is what the basic equations. And as far the procedure is concerned, the finite element method basically it is having a lot of advantages. Okay, if you list out the advantages, so we have so many advantages are there. We can solve any complicated problem. That is one. Second thing is it is very flexible because we can apply this to solid mechanics, thermal, okay, all fluid mechanics, all domains you can implement. The third one is the most important thing is well structured procedure, systematic way. Therefore, because of this, we can automate easily. So these are the advantages of finite element method. And this is a basic equation. We have a step-by-step procedure. If you look at the procedure, it's very smooth and systematic. First, domain discretization. Then select the element type. When you type when you select the element type, shape and approximation, these two are very, very important. And derive element equations based on different methods are there, variational and energy methods and other methods also there. Then assemble element equations to form global system. There are two elements are there. For each element, you have to derive the equation. There are two equations and you have to assemble two equations. Then that is what global equation. Once if you know global equation, then what you can do, identify boundary conditions, initial conditions, implement on your final global equations, and then you have to solve for field variable. If I say field variable, it can be anything. It can be displacement or temperature, depending on what kind of problem you are going to solve. Once if you know field variable, that is what we can say, let's say displacement. That's what primary variable. Once if you know displacement, Then using that, you can find out secondary unknowns, that is stress and strain. So if it is a solid mechanics, what we do first, you are going to find out first displacement. Let us say two nodes are there in our analysis, node 1, node 2. You are finding U1, U2. So this is all primary variable you have computed. Once if you know primary variables, then I can find out the stress. How do you find out stress? From Hooke's law, Young's modulus into strain. What is strain? du by dx. That is equal to Young's modulus into what is du? Change in length, change in displacement. What is change in displacement? Displacement at 2 minus displacement at 1. U2 minus U1 is strain by original length. What is the original length of this is L. This gives us stress. Okay. Of course, strain is nothing but this only. This is what we call it a strain. Okay. So there are two matrices here. One is B matrix. That is nothing but strain displacement relation matrix. Another matrix is D matrix. This is what? Stress strain relationship matrix. These two matrices are very, very important in solid mechanics. Okay. And in elementary strength of materials, you might have learned about strain displacement relations. Okay. It depends on whether 2D or 3D. Okay. So if you say strain X is nothing but du by dx, and strain along Y is dv by dy. Strain along Z is dw by dz. These are the normal strains. Apart from this, you are going to have shear strains also. Okay. So that is how you need to find out the strain. First displacement, from displacement strain, from strain stress. There is second variables you are going to find out. Procedure is same. Whether it is one dimensional or two dimensional or 3D, this is a systematic procedure. Okay. And this is another important thing one should know about the common sources of error. The common sources of error. Basically, the finite element analysis is an approximate. Just first thing you should remember that it is an approximate. So whatever you are going to get from the FEA, then is an approximate tool. But you should know that whatever you do, like if you do any major mistakes, otherwise solution will be done and you will get some result. But you should know what is the validation of your result, whether it is working correctly or not. You need to do the validation. Before validation, you need to do the convergence. That I'll show you how to do that. Okay. What are the common sources of error in FEA? The first one is domain approximation. If you don't do domain approximation, then it yields wrong only. Because I told clearly, the critical sections, wherever there is a critical sections, I think I told one case, and also in case of shaft, particularly one example in case of shaft. Okay, design of shaft, the presence of shaft is wherever there is a power transmission, you can see the shaft, right? So here, the power transmission with the help of other elements such as pulleys, gate drives. This is a shaft, the supports, bearing 1, bearing 2. So here, I'm going to attach one pulley to this. How you are going to attach pulley to the shaft? You are going to attach these two with the help of key. With the help of key. So key is a rectangular key, let us say like this. How we are going to keep this? For this, what you are going to do? You are going to make a slot in shaft, and also you are making a slot in the hub of the pulley, and this key 50% top, 50% sits in the slot provided in the pulley. Remaining 50% sits in the key provided in the shaft. So you are connecting them using key. So providing a keyway slot is very common in this. If you provide keyway here, what you are doing, you are removing the material. That means what there is a sudden change in geometry. The stress concentration will be more in this. So what you have to do when you do the domain approximation here around this, your meshing around this should be very fine and accurate. Then only you can predict results appropriately. These things are very important when you design, when you do the FE analysis of the critical sections. Element interpolation approximation. This is also very important. You need to select the proper interpolation function. If you don't select proper interpolation function, you may not get your desired results. And numerical integration errors. Generally, when you do the numerical integration errors, the lot of digits will be there, spatial and time integration. So there also may cause error in FEA. And the computer errors. For example, the values, if you take rounded up values, if you don't take more digits of the decimal, it may also lead to an error. Okay? And this is the one important thing. Accuracy, convergence, increases. These three are, okay. 1 and 2 increases, the error tends to 0. So first two are very important. What do you mean by accuracy? Whatever solution you are going to get from FE, FEM, then you are going to compare with exact solution. This is what the error is. Generally, what you are going to do is, we are going to express this as an error percentage. So for error percentage, what we do, same thing only, exact minus FEA by exact into 100%. In terms of error, we should express the error. This is what the accuracy. And what do you mean by convergence? This is very, very important, convergence. This limit of error. Convergence means what? You are limiting the error. For this is very important. How do you do this? There are two ways of doing it. One is number of elements you have to increase. That is called H convergence. That means what? If I take 10 elements, your result is different. If I take 50 elements, result is different. If I take 100 elements, result is different. That is what H convergence. You need to increase the number of elements, but you are not changing the order of the shape function. Or second approach is increase the approximation order, P convergence, but number of elements you are not touching. Only you are increasing order of this. How do you do this? You can do this, I think, in finite element analysis. I think many of you might have done this. How we are going to do that? For example, if I select the beam element, I have selected beam element. Let us say I want to show the option. So I am doing this beam 2 node 188. I have selected beam element. Then here, if you go to the options, are you able to see the screen? ANSYS main screen. Are you able to see? Okay. In options, if you go through options, here, these are very important things. Try to use all these options. If you look at the first one, degree of freedom, by default it's showing 6. That means what? You have 3 translations, UX, UI, UZ, 3 rotations, X, Y, Z. Sometimes, if you handle with thin walled sections, maybe shear center, unsymmetrical bending, thin walled sections if you use, then what you have to do, you have to select 7 degree of freedom, 7. One more is called warping. See, 6 plus 1, warping. The warping is a phenomena generally we can see in case of thin walled sections. The plane section, it will undergo like a wavy kind of things. The plane sections will not remain plane. That is what warping parameter. The warping parameter you need to include particularly when you are handling with thin walled sections. That is one thing you should know. And also, you see that the element behavior K3. So if you click this, you have 3 options. One is linear form, quadratic form, cubic form. If I take linear form, you told just now we have seen that the order is lower order. I'll get something else. Same problem if you solve by using quadratic, you are increasing the order. That means what? Your accuracy will be improved. If I go select third one, cubic form, still you are going higher order, therefore accuracy is still more. This is what I'm talking about the error, how you can improve. Order of shape function you are going to increase. So this you need to try. Then only you can see the difference. Not for simple problems. If you try to solve complex problems, then you can see the difference when you're moving from linear to quadratic, quadratic to cubic. This is what you should know when it comes to convergence is concerned. Okay, so whether you can increase number of elements or you can increase the order. Okay, and both increases, ideally, error tends to zero. Remember, error tends to zero as number of elements or approximation order increases. Okay. But only drawback here, if I take more number of elements, computational time is more resources. Similarly, same increase order, it also same thing. But there is a, you should know where it is converging. That is very important. Therefore, when you do the finite element analysis, always you should remember two things: validation, convergence, of course, accuracy. These three are very important. If you try to solve problem by using ANSYS, right, without validation, it is not accepted. Without convergence, it is not acceptable. You need to do the proper validation, because whatever you do that, then you'll get something. But you should know whether it is valid or not by doing this. So first thing what you should do, you should do the convergence. So let us say this is a one plate problem here. The aspect ratio is 0.05. When I try to solve by using number of elements 101, the solution is 42.73. If I take 42.73 and proceed, then this is not correct. You should know whether it is a converged or not. You should check. How do you check? Increase number of elements 101 to 145. Now you see the answer 42.73, 42.40. There is a change in your answer, right? Again, increase the elements. The value is changing. That means what? It's keep on changing. Now, if you look at this, if I take number of elements 1405, I am getting 41.13. And compared to previous one, 41.15, the second digit after decimal is changing. Now, if I take number of elements 1711, it is coming same thing. So this is what converged. That means what? ANSYS basically is approximate, but when you approximate things, you do the better approximation. That's what I meant to say. 41.13 is the correct one. Like this, you need to do the convergence. So this you can do, whether you can do for all cases or only one case, as long as your geometry is not changing, this is valid. You can provide hole and everything, this is fine. So I can take directly 1711 and do the meshing and proceed. You will get converged value. That is one thing you should check. Second thing is comparison of your results. You need to validate your result. How do you do the validation? The validation you can do in three ways. One is conducting experiment by yourself, or if it is not available, you check whether it is already available in the literature or not. You compare, validate your result. Or if exact solution is available, you validate with exact solution. Or if somebody done same problem but using some other technique, you do the validation with that. Okay, or publish the results. Any one of the above. That is how we need to do the validation. So you see here, there is a validation here. This is our result, and compared with the other. See, you have to compare the error also, how much is coming, because the method may not be same. We are using one approach, they are using other method, but you see whether they are closely coming or not. Okay, so these two things are very essential. You should know convergence and then validation. You should do that. And this is what I'm trying to say. This and this is not accepted here, because around the hole you are taking only normal mesh, but you should do refined mesh around the hole. This is a refinement you should do. Okay, that is very important, particularly for the critical sections. And for the bar element and beam element, these basic things you know that. Okay, and this is for 2D triangular element. And here it is scalar value pi1, pi2, pi3 at 3 nodes. And here you have a vector tensor at 1, u1, v1, at 2, u2, v2, at 3, u3, v3. Okay. And these equations, proportion equations, basically the finite element equation can be solved using the three methods. Either the first one is direct method. The direct method is only for simple cases, okay, based on physical reasoning, and limited to simple cases. Okay. But for complex problems, what you can do, you can use either variational virtual work method, wherein It's based on concept of virtual displacements. It leads to relation between internal and external virtual work. That is, sum of internal work and external work should be equal to 0. And to minimize the system of potential energy for equilibrium. Or you can use weighted residual method. So here in this method, you're going to get some error. Then that multiplying with the weighted residual and integrate over this and equal to the 0. And that is how we are going to implement this weighted residual. Here we have different methods like collocation method and least square method, yeah, and Gallatin technique. Okay. You can use these techniques. That is second approach. And the first thing is what we to do should know. We have to derive the stiffness matrix even for spring element or bar element. This is what the stiffness matrix for spring element, and this matrix is what we call it as stiffness matrix K, and U1 U2 are called nodal displacement vector, and F1 F2 is a nodal force vector. That's for the spring element. And this is what the I'm trying to show in ANSYS approach, right? Linear, and this is quadratic. In quadratic, you are going to get one more point in between first and last to have a better control. In cubic, you can see two more points in between. That is how we are going to increase the accuracy. See here, the straight. We have only first and last, in between no. But here one more point in the middle. Here two more points in the middle. So this curve is going very close with this. Okay. So similar kind of things I can show you how your the results are varying with respect to the shape functions. See, if I take a linear, this is our exact. Yeah, this is our exact. But if I take only one term, right, it's constant, then you see there is a huge variation between this and this. If I go to linear approximation, and this is your exact red color, and this dotted line is your, you are not following this, but you are going along this. If I go to next order, see the red indicates exact and this black indicates quadratic. If I go to cubic, it will come very close to the exact. That is how we are moving from one to very close to the exact. So that is how the shape function is having following your exact when you increase the order. This is a basic equation. This anyway, I am going through this. Only one thing. This I like to explain this for whatever element may be. One thing is procedure. Basic procedure is same. Only thing is the stiffness matrix. This is going to differ. A well -1 1 1 -1. This is going to differ. Okay. If I look at only 2-noded bar element, this is different. If I take a 3-noded bar element, stiffness matrix is different. Okay, and use that equation for your problem and proceed. If it is a beam element, stiffness matrix is different. This is one thing you should know. That is K stiffness matrix for element I'm talking about. And U1 U2 is for nodal displacement vector. You see here, there are two components are there. This is very, very important. There are two components are there. This is what the external load, P1, P2. The loads which are acting at node 1 and 2. Let us say this finite element equation is for 2-noded bar element. 1, 2, you are applying this. Okay. And 1, 2 nodes and element is 1. Okay, generally the notation is concerned, nodes use number without encircle, element within circle. one node, sorry, one element, there are two nodes are there. Okay. So for element 1, this is the stiffness matrix, and these are the nodal displacement. That is why you are going to have U1, U2. The P1, P2 also nodal force vector 1 and 2. See, this part is called self weight. Sometimes self weight can be ignored. No need to consider this term. If the self weight is also considered, then you have to include this term, density term. Then this you have to include to the, add to the external load. Okay, these two terms are very important when you write down the equations for finite element equations. Now we have a lot of flexibility when you try to solve any problem in using any tool, ABAQUS or LSDN or ANSYS. Only one thing you should remember: our background equations. It solves simply, but how it is solving background every step you should understand clearly. And also, if you see for every step there is a the coding part also, you can see that how it is going to vary. If you understand the coding part, you can clearly understand how every step is going on. And because of a lot of flexibility using coding in other languages, what you can do, you can write your own code and you can try to implement either using MATLAB or Maple or Mathematica, and Python also we can implement. It's very easy. Only little bit of changes are required. You have a lot of flexibility. Okay, you can try using any one of these. Mathematica, in fact, that is also very useful tool. Mathematica, highly mathematical oriented things, and coding size you can reduce very limited because of high inbuilt functions are available in Mathematica software. So this is what general equation. Only thing is this is going to change from element to element, and this is self weight and this is external. Is only thing, and you can proceed accordingly. And this is I told this three noded quadratic approximation. Now see here, this is two noded. What is this is a linear approximation. Two noded. This is what our stiffness matrix. Same thing. If we move on to quadratic, what is changing here? One more is coming. 1, 2, and 3. So this is our stiffness matrix. The stiffness matrix is changing. That's what I told clearly. So this is going to change. This is what stiffness. When you move to beam, again, you need to derive the stiffness matrix. That derived matrix you can use to solve the problem. Now here, I'll tell you how we are going to solve the problem. Here, if you look at this, as per discretization is concerned, before you solve the problem, properly understand the physics of the problem here. And left side, there is a support. Let us call, generally, node can be represented without numbering, 1. And here, there is a change of material. So let us, this is 2. At the end, there is a load 3. 3 nodes. Elements, 2 elements. Okay. Connecting node 1 and 2 is element 1, 2 and 3. Now what you have to do, you have to write stiffness, finite element equation for element 1. That is this. Similarly, you should write down the finite element equation for element 2. That is this. Okay. Now what you have to do is, you have to assemble these two to get the global system. Okay. How to do that? For doing this, what you have to do, first you should know what is the order of this matrix. How many nodes are there? There are 3 nodes. So here you are going to get 3 by 3 matrix. I'm going to get 3 by 3 matrix. At each node, 1 degree of freedom. There are 3 nodes. Therefore, I'm going to get 3 by 3 matrix. Right? Okay. How you are going to get this? Here, let us say this is 1, 2. This is 1, 2. 1, 1. First value, 1, 2, second value, again, 2, 1, this value, 2, 2, this value. Here also you can make 1, 2, 3, and here 1, 2, 3. And once it is done, again move on to the right side. Here we have 2 and 3, element 2. So this is 2 and 3, and this is 2 and 3. 2, 2, 1. into AE by LE. So already one value is there. You have to add this value to previous value because 2 is common. The node 2 is common between element 1 and 2. Then again, 2, 3. 2, 3 is this element. Again, 3, 2. 3, 2 this and 3, 3 this. Now you see here, this element you are getting 2. Why? Because 2 is sharing between element 1 and 2. And this is U1, U2, U3 nodal displacement, and these are the external node. This is how you have to write down this. And once stiffness matrix is ready, you should be able to understand clearly whether the stiffness matrix you have derived is correct or not. You need to check. For checking this, there are 3 things you should know. One is the stiffness matrix should be symmetric. Check. Yes, symmetric. Second one is, it is symmetric. Second one is, if you add all elements in the column wise, the net value should be 0. The net value should be 0. That is the second check. The first one is symmetric, it is satisfied, and add all the columns. Column wise, net is 0. So if I add this equal to 0, if I add all these things, net equal to 0. If I add all these things, net equal to 0. That is second check. Third one is that diagonal elements should be positive. See, the diagonal elements should be positive. Yes, all are positives. Also, in the diagonal elements, if I take this element, that should be higher than other elements present in the row. This is higher than this and this. Similarly, this diagonal element is higher than the second row of the other elements. That also you need to check. Once it is fine, that means what? Your calculations are right for the stiffness matrix. Once if you know global stiffness matrix, I should identify boundary conditions. I should identify boundary conditions. Boundary conditions are very important. What is boundary conditions? Look at this. At node 1, what is there here? Support is there. So when the support is there, displacement at node 1 is 0 because support is there. So U1 at this point is 0. Now U2, it will be there. U3, it will be there. Fine. Then, what about forces? The force at node 1 is 0. The force at node 2 also 0. Then, at node 3, there is a P is there. Therefore, P3 equal to P. These are the boundary conditions. And substitute these boundary conditions in your global stiffness matrix and find out these values. U2, U3. So U2 is this and U3 is this. So I got U2, U3 nodal displacements. If I get U2 and U3 nodal displacements, I can find out stress in element 1, stress in element 2. How to find out this? Stress in element 1 is Young's modulus of 1 into du by dx. This is equal to E1 into element 1 is U1, U2, right? So it should be U2 minus U1 by the length of the element 1. The length of the element 1 is L1. Similarly, sigma 2 is, I should write U2 into du by dx. That is equal to E2 into, for element 2, what is change in length? U3 minus U2, U3 minus U2 by its original length is L2. So that is how I have computed stress 2 also. Like that, each and every element I can find out stress in element 1 and element 2. Okay, that is how we are going to calculate this. Okay. So for the beam, that also same thing. For beam, you are going to have displacement as well as rotation. Okay. That is the fourth order we'll get, and procedure is same. Only thing is stiffness matrix is different. This was stiffness matrix. For the beam element, stiffness matrix is different. Only that is going to take, and accordingly you can calculate. Procedure is same, basic procedure. Okay. Once if you derive this stiffness matrix at element 1 and element 2, you have to assemble these two. When you're assembling, you are going to get matrix like this, symmetric about this. Always, once we get global stiffness matrix, please check it is satisfying basic things or not. First one is diagonal element should be positive. Second thing is it is symmetric. Third one is if I add all elements column wise, net should be 0. That you need to check. Impose boundary condition. Solve for first, you are going to calculate nodal displacement. Then other things you can find out, stress values and other things. So that is what you are going to solve the problems. Okay, this is what the basic things you can do for frame element, truss element in the similar way. Okay. So this is what the basics introduction to finite element methods. And anything up to here, do you have any doubt? This. I'm going to explain case study 1. So this problem is numerical simulation of detonation shock dynamics and its effects on pressure wave propagation in underwater explosion scenario. So this problem, actually, this work, one part of the work we have done, and the second part we are doing now. And I'm going to explain you what is this. This area is slightly, is a different topic. It comes under explosion scenario, and how we have solved this problem, and I'm going to explain you in this regard. So basically, when you're storing explosives, right, either in terms of unit or as a whole, the precaution is very, very important. Generally, when they store all these devices, what they do in godowns, they have a separate units out there, separate units. Let us say here, they won't keep entire in one location here. If they keep here, because of they'll have a compartmental wise. Here, explosive 1, maybe unit wise or in 3, 4, 5, like that. Suppose due to any reasons there is a blast of the unit 3. So whenever there is a blast in unit 3, that effect should not damage unit 2 and 4 and adjacent things. You have to minimize that damage so that we can safeguard the other units because they're very expensive, and also safeguard the environment, people working around the area. So this is what the main aim for doing this this kind of work. Okay. Therefore, safeguarding machinery as well as people and is a first important criteria. And in this area, a lot of work is going on for so many years, continuously is going on. So what we are going to do here, whenever there is a blast, let us say unit 1, then it should not affect the unit 2. So in between, you have some safe zone. Okay. So this is what interface. Suppose there is a blast here, the effect of blast will be measured up to here, this transition. If I know this distance, I can design this part accordingly by keeping some margin. So only this unit is going to destroy or get affected without damaging the adjacent thing. That is what we are trying to do this. So basically it comes under blast. The material is subjected to shock wave. That is a impulsive load, behaves differently compared to material behavior in static load. The first phase we have done the blast in air. Okay, undertone. If you keep landmine up to certain distance, if you blast, then how it is going to damage the vehicle which is traveling over this, particularly in war scenario, how it is going to damage, what distance it is going to affect that vehicle. That part you have done. The second part is underwater explosion, particularly in marine related things. This is very, very important. Whenever there is a blast in underwater, then there is a effect up to certain distance. Beyond that, effect is nominal. The deformation, everything within elastic limit. But near to the blast zone, the effect will be very severe. So how to find out this transition? It is called near field, far field. Near field means if anything is there within that circle, the damage is very severe. Far field is nothing but if you have any unit over there and damage is minimal. So here trying to find out what is the transition distance. This what the study all about is. So basically this is a impulse load. It is defined as a load that changes the momentum of an object. Okay. Basically the integral force with respect to time. The loads that marine structures encounter during wave impact. So this comes under this impulse load. To understand such complex behavior, the knowledge of phenomena such as generation of shock wave, how it is going to propagate in various medium, maybe air or underground or the water medium, this is very important. So first, initiating shock and how it is going to propagate and what is the effect of this wave through its travel. That is what is important here. Basically, this is in context to the chemical explosion. Generally, the explosion with respect to nuclear, mechanical, chemical, here the focus is chemical explosion. We keep the chemical explosion and initiate the blast, and during the blast, how the waves, heat generated, how the wave is traveling. That is what we are focusing on this. The chemical explosion basically it is caused by an extremely fast conversion of a solid or liquid compound into hot gases, having a much greater volume than the substances from which they are generated. Basically, any chemical compound is a mixture or device having a primary purpose to function by an explosion could be named as an explosive. So in this explosion here, they are basically high energetic substances with fast reaction rates and can be in any form, gaseous, liquid or solid form. Okay. Many different types of explosives are in use with different strength and signatures. And protecting the devices is a good understanding for this. One should know the good understanding of the explosive phenomena, that is what it is and what happens in an explosive, where burning initiation, finishing with studying the interaction between shock waves and structures. Here, fluid structure interaction because of the blast. Particularly, we are talking about the blast in underwater phenomena. So here, numerical modeling performed, and also how the determination parameters are determined by specific properties of an explosive. Further, propagation of shock in water. This is what you are doing. And if you look at the blast in water, it looks like this. What is the depth of the blast from the surface of water? Accordingly, these waves can move in all the directions. The waves, whatever is there above the water level, can be seen like this. The same way, and the propagation will be there in other directions also, horizontal direction into the depth direction. And also we can see the severity of this effect, maybe vibration and shock, all things you can see if it is a near field. And if you're away from this, you can sense, but the effect is not that much severe. This is what the explosion in underwater. Okay, so same way same phenomena will be there in all directions towards the depth and the left and right side. Okay, and this is what the near field. Whatever things we are seeing, the near field, trying to measure using devices what is the effect of this blast in underwater explosion. Basically, the explosion two types. One is the exothermic and endothermic. In endothermic, this is it cooler than the surroundings. The second one is exothermic. This is hotter than the surroundings. We are talking about the second one, exothermic. Okay. Here, in this case, the numerical analysis is a coupled treatment of detonation in case of chemical explosions and its effects on the surrounding medium by the fluid structure interaction. We call it as FSI, fluid structure interaction. How the effect will be there with the solid, because through the fluid, because the wave is traveling through water. How do you say the shock wave? Basically, the shock wave, we can define it is caused by a body moving supersonically in a gas or by a detonation. The shock wave or a shock is a type of propagating disturbance created in a medium. Therefore, here we need to understand that how it is carrying energy, how it is propagating through medium, how it is characterized by an abrupt, nearly discontinuous change in pressure, temperature, and density of the medium. So with this, how these parameters are going to change. Pressure value, temperature, and density are changing through the medium. And if you look at this, the speed of the sound, if it is initiating, it is traveling like this. You can see here, the speed is traveling in this. And if it is sound, approximately in air, it is 331.29 meters per second. It's the same in water, it is 1480 meters per second if it is water. And it is traveling like this. See, initiating here, it is traveling like this in the second. This is what how it is traveling in air. There is a magnitude and how it is traveling. And if you measure this, the top surface, the value is 1500, and the depth, if it is going, minimum is up to here, up to 1000 meters. The minimum velocity of the sound is this much, and still if you go in depth, it is increasing and increasing further. And the detonation wave, basically, you can see in this process here. Basically, the water density is 997 kg per meter cube, then air 1.225 kg per meter cube. Therefore, the blast in air is entirely different from blast in water because of the variation in density. Because of water density is higher than the air, therefore, which increases inertia of water, as well as it is harder to compress by pressure. Whatever wave is there, it will act very good conductor. Therefore, the water is a good conductor of the shock wave for long range. One shock wave is coming, it takes and it just transmits to the long distances. That is why the water is a very good conductor of the shock wave for long range. Then, in this process, the effect of underwater explosion depends on explosive characteristics and the distance of structure from detonation point, that is near field or far field effects. That's what we are going to study in this process. And this is very, very important. Basically, nearby any ship is there is a blast close to the ship, then how it is going to damage that ship or any marine structure. That we can study if you know this this effect, far effect and near effect. So there are several phenomena during underwater explosion. There is a series of events such as severe fluid structure interaction, effects on target, shock wave propagation, how it is propagating, cavitation, bubble formation, and water jet effects. Basically, the bubble formation, we don't need to consider because basically water is incompressible, right? Therefore, the formation of the bubble effect can be ignored. Okay? And water jet effects, these are these series of events. And these underwater explosion leads to devastating effects on the particularly marine kind of structures. So up to some distance. So that distance we are going to find. So here what we have done, we have solved this problem in two ways. One is using LS-DYNA and ANSYS and DSS-DYNA software code. The DSS-DYNA software is a in-house developed code and solved the problem using DSS Dyne, and we have validated with the published result. So here, how the shock wave is initiated the center and how it is traveling. Then studied the temporal and spatial behavior of generated pressure waves in underwater explosion. Okay. So we have taken three explosives: SEP, TNT, and PTN. They are the explosives. Okay. And these explosives are very powerful. They can damage the structure, right? And we can predict how they can potential damage to the nearby structures, okay, by following gamma law of their expansion of detonation products after explosion, and study the changes in parameters like mass parameters and weight, diameter of explosives, and we also studied what are the far field and near field effects of the underwater explosion and establishing clear translation between them. Okay. So what is the translation between near field and far field? Is there any relation exist? Suppose there's a blast here, it takes time, so that we can move away from the translation range within time. Therefore, we can safeguard the structure. So this is what advantage of these kind of studies. So here, out of three things we have taken: SEP, TNT, PETN. So TNT, it is a detonation velocity is 6,900 meters per second. Travels very high speed. Once ignition, once it is initiated explosion. And PETN also, it is having almost 8,500 meters per second. It is something like a RDX. They have very high potential to travel with high speed and damaging nearby structures. And SEP is basically 65% weight PETN and 35% weight of paraffin. So these are the almost belongs to same family with different detonation velocities. Okay, this is what the scenario. This is a spherical detonation wave. So here, this is what the explosion with the red color, and outside one is a medium, water medium. So once it is explosion takes place, then the detonation wave generating like this, and it is traveling in this direction like this. It is traveling and moving around the sides and the bottom, also the top, and in the process there is a transition zone up to here. This is what is a zone, is critical zone, because it is having near field effect. Once it crosses a certain distance, this is far field effect. So damage is minimum. So what we have to do here, you need to identify what are the transition from near field to far field. This is what the modeling of this spherical detonation. Okay. So red color is the source of the explosion. It can be SEP or TNT, PETN. All three units are tried for this. And for solving this, different models are there. One is CZ theory. Okay, one is called CZ theory. Deals with energetic characteristics of detonation waves. It release of energy in chemical reaction is complete and instantaneous, with shock moving through explosive compressing, heating explosive to activate chemical reaction, resulting in formation of detonation front to propagate with constant detonation velocity. It is called CZ velocity. Generally, the detonation velocity generally lies between 6,000 to 8,000 meters per second. Generally, for these group of substances, mostly one is 8,750 is higher than this. and another one is 6,900. Mostly comes under this group. And here you see this propagation here, burned, unburned. The burned properties are this: pressure value, density, temperature, enthalpy. Unburned, pressure value, density, temperature, and enthalpy. Okay, so this is what the propagation of detonation trend. And also JW equation of state. So for this analysis, we have used JWL equation of state. So JWL equation of state, which is used for predicting the properties. So here, there are three persons developed this equation: Jones, Wilkinson, and Lee. They have proposed this relationship between the detonation products expansion. Okay. So a lot of parameters are there. The parameters also is given. This is what equation proposed by them. Here A and B are the pressure coefficients. This is not a mathematical equation. It is an empirical equation. So where the constants have been derived by conducting a series of experiments. Okay. So here the capital V stands for relative specific velocity volume, V2, V0, which is independent variable, and A and B are the pressure coefficients. Capital A, capital B are the pressure coefficients, and R1, R2 are the principal and secondary parameters to depict short range and long range behavior of the respectively. You can see the values here for different substances. 1, 2, 3. This is empirical relation I have told. So that's why we have values A and B. Here also A and B, and here also A and B, because these are the empirical values. These set of values. Are you able to see this one? Now this is another model. The basic equation of state is given like this. Here also there were separate parameters for this. For each one, values are given. Density 1000 kg per meter cube, C value 1484 meter per second, and gamma naught. These values are the already established by conducting a series of experiments, and the properties are given using that equation derived for these four substances. Okay, and for these properties are there already. We have a density of these properties already we have, and using these values and A and B and R1, R2, omega 1, E1, all these various parameters are established, derived by using JWL. Okay, and these values only we are going to use to model this. Okay. And also the properties, basic properties of these three are density and detonation velocity and CZ pressure values. And if you look at the values and density wise, if you compare, density of this is higher than, and this is higher than this. Okay. So this is what density wise comparison. But out of these three, we can also compare which is the best one by plotting all these three. Okay. When you plot all these three in this plot, that is a log P versus log V relative velocity, V by V naught we have studied, right? They are the curves you got 1, 2, 3, 4. So before you proceed, always what you have to do, try to plot all these substances you have selected. Then out of these four, which is the best one that we can use it. So this gives area under the curve. If the area under the curve is maximum, you have more work. Okay. Area under this curve is less, you have a minimum work. Accordingly, you can choose. Okay. So if you look at this comparison is necessary before you go for the selection of particular thing. And it is also necessary in identifying nature and comparing strength of explosives used in numerical analysis. Okay. And basically, these curves are reversible adiabatic, that is isentropic in nature. The expansion process happens so quickly, and now we can compare them. Out of all these things, you can see SAP, and there's a which is having largest gamma, therefore value showing steeper curve but least work done. The less amount of energy will be released. That means what you see here, this is what I am talking about, this one, SCP. So this steeper value. So remember, with highest gamma value, if the gamma is highest, the curve will be like this. So for this, gamma is highest. But you know, this area is less compared to other things, shaded area. That means what? It gives minimum work. It gives minimum work. Less amount of energy will be released. Okay. While C4 is having least gamma value and large area under the curve. So if you look at the C4, this is C4 here, top one. So the area is more. That means what? More energy is going to release. Okay. Therefore, SEP low energy is going to release, and this is going to release more. And in between, other two are coming. PNP, PET, and JW curves are moderate in nature as compared to the others. So this is what the selection, which is you want more energy, accordingly you can select from this. However, in our study, what we have done for all four, and we have compared the how this transition is going to take place from near field to far field. But for the selection, you should have to select one which is the best, where you are getting more work done and more energy is going to release. So they are the values of gamma values, I told, right? Phase 1, phase 2, phase 3, and these are pressure values for all four substances. Then basically the water is incompressible fluid, hence expansion volume of the bubble formed in the underwater explosion phenomenon is negligible. That's I told, right? Bubble formation, and once a bubble forms and again bubble explodes, that effect is very small because of its incompressible fluid. Okay? And therefore, in case of underwater explosion, JWL curve parameters are restricted to only first zone of expansion process. So that is what the restricted to only first zone. And for numerical simulation of far field effects of underwater explosion, instead of JWL equation of state, P for gamma formed by using parameters in the first zone of JWL curve can be used for reducing complexity of JWL, and engineers and other scientists are more familiar with the adiabatic expansion process than JWL. Therefore, implemented adiabatic process, accordingly computed the values based on initial pressure value, and first phase curve index is gamma. Then this is what the simulation part. So here, first what you have done, we have done the comparison of this, benchmarking of this. So we have taken 1/4 model due to symmetry. Then to save time and time for computation, and also lot of data is going to generate, so it can save the resources quickly. You can get the data whenever you want because of the ANSYS symmetry. So first we have taken PETN, explosion of radius 50 centimeter. This red color, this entire radius you have taken 50 centimeter, and it's 1 kg, because 1 kg releases huge amount of energy surrounded by the infinite water medium. When you are assuming that, compared to this surroundings, you need to assume the infinite. You can't keep a limit for this infinite medium. The analysis done with LS Dyna and DSS Dyna, and LS Dyna, and then we are doing now with ANSYS. LS Dyna, DSS Dyna. The DSS Dyna, I told already, this is a inbuilt software, and that we are benchmarking, and also we are continuously working. It is matching well with the established results that I'll show you. And here ALE meshing is used because of its mesh rezoning capacity. Because ALE continuously, when wave propagates from here to here, continuously you need to change all the parameters. For that suitable meshing option is ALE that we have used in this. Okay. Now you can see that the parameters are studied. The accumulated pressure and kinetic energy constitutes work potential of explosion. See here, first one, 1 microsecond is this. Second one, 2 microsecond. Third one, 3 microsecond. How it is going to propagate? This is fourth one, 4 microsecond. 5 microsecond, 6 microsecond. How it is propagating? Are you able to see this 1/4 model? Are you able to see? Yeah. So with respect to time, that is how it is propagating. The wave propagation I'm talking about. Once it is initiated, 7 microsecond, 8, 9, 10, 11, 12. It is just propagating, and in the process we have extracted the data and plotted result versus time. You can see clearly from this plot. Total I told how much it is radius, right? We have started from the center. Total explosive radius is this, right? This radius is 50. So center point is this. Center. At the center, this is the curve, pressure wave, generating and moving like this, traveling like this. And next to 10, at 10 mm from the center, this is the curve. How pressure is going to increase and traveling like this. And at 20, center is over 10, 20. At 20, pressure is increasing up to 15 GPa and coming like this, how it is traveling. Then 30 is coming, and 40 and 50. What is 50? What is 50? This is entire radius, right? 50 is nothing but at the outside of the explosion, right? So here water is there. This is explosion. So 50 means what? It is an interface. This is interface. So at 50, it is coming here. When it reaches 50, the next is only water medium is there. No explosion. Entire explosion takes place. Then only water is there. Now entering into water. Therefore, up to interface, this is what? The rise in pressure. How much we see here? This is around 15 to 18 in between, close to 18. Up to that, the pressure wave went and again coming like this. Now we can see that up to interface, the pressure is very high. So this study is confined to within the explosive. Then you will see within the explosive radius up to interface. Okay. Now this is how density is going to vary through this. So for 2 microsecond and 5 and 7 at different time intervals, that variation of the density, because when explosive takes place, then continuously there is a change in density, right? That value is how it is going to vary, that part. So you can see in the beginning more, then again at 5 coming down, again here it is coming down. Then how much energy is going to release? Total for PETN considered 1 kg in water is observed to be 1.3 megajoules, out of which 4.7 megajoules of initial internal energy, which is nearly 30%, which indicates work potential of explosives. That means out of total amount of energy released, 30% which indicate the work potential of explosives. Then what about remaining 70? After 6.6 microsecond energy, transfer rate is rapid and shows whooping down trend. Water absorbs 70% of energy released by explosive. Therefore, out of 30% is potential of explosives. Remaining 70% energy absorbed by the water. That is what the sharing of this. So this is released by explosion, out of which this is in explosion and this is in water. This is total. this is in water, this is an explosive. That's how energy released sharing in the for PETM of 1 kc. Now you see pressure variation. We are doing pressure variation in water now. So started with 59. Of course, 59 is within not in water, but showing for comparison. This is 50. So showing up to 49 means just before inside the outer periphery of the explosion. Then shown interface. Then you see 52. Once it is coming into crossing interface, now the pressure value is going down. You see, going down, going down, going down. All things, why? Because that water conducts, it absorbs energy and it is traveling, okay, smoothly. It's a better conductor of shock energy. That indicates how the pressure is going to change. Therefore, you have seen within the explosive how much pressure is going, and in water how much pressure, variation of the pressure is going. So this is a variation of the pressure. Now you can see the velocity also, like velocity variation in water is here. At 49 very high. Interface is this. Once in the water, now you see how the velocity, but compared to pressure velocity, you can see here values, how it is going to vary. The shock wave traveling through water medium. Okay. Then now you can see the validation of LS dyna and DSS dyna. These two. So this LS dyna is published result, and whatever we have done using inbuilt code DSS dyna. So the values are matching almost. The trend is same for the pressure wave propagation. Similarly, for velocity also it is showing same trend. Slight variation in the values, but trend is same. So it is also matching well. And also, this we have compared with the published result, which they have done by using LS dyna, which is public, available in the literature, with our results. You see the pressure wave is almost same trend and matching. The benchmarking, we have done this. And also, see this variation is velocity. Velocity variation also matching very well. They're almost same trend. Slight variation is there. Okay. This is what we have done. Now, we have done two different scenarios. One is heterogeneous explosion. Another one is homogeneous. Only difference between these two are, this is heterogeneous. That means what? It is not takes place at one instant, initiating, traveling, and propagating to up to here, then traveling through water here, and this is what the variation of the pressure here, then how it is reducing. So JWL equation of state we have used here. This is a peak pressure variation. This is what is heterogeneous. Okay? And this is burned and this is unburned. This is how the burning takes place and traveling away from the center of the thing. Inside is burned, outside is unburned. And this red color indicates burning. This is a heterogeneous process. For heterogeneous, and that is second model is homogeneous. In homogeneous, explosion start from the complete burnt product of gas. Suddenly, all things, then it travels. Okay, and these two we have done for both things to know the interface. And this is what I'm talking about. Homogeneous. Okay. Now, the last thing is near effect, far field effect. The main idea here is near effect means if anything in that zone can damage severely. This is what near field. It comprises sudden high pressure generation of shock waves, causing severe damage by local deformation with rupture of the joint, structure or system. This is due to buildup of high pressure inside the explosion medium upon detonation with respect to CJ theory. So this is very, very important. you should know what is the near field effect. If any system is within near field effect, that is over, and it will damage severely. That is what near field effect. What is far field effect? In far field effect, the intensity of shock wave gets reduced with distance exponentially, and beyond certain point in water region, it only elastically deforms structure without much damage to the system. So these two are very, very important. Now, there is a strong need to segregate near field and far field effects. That is what the next part is. So what are the clear transition between near field and far field? If you know clearly, then we can design these explosive systems in such a way that whenever there is a blast, nothing will damage to the nearby structure. If you keep that in far field, then we can safeguard everything. Only that unit alone will be destroyed without causing damage to the adjacent units or to the entire system. So both models have done for all these three by changing charge radius 20 mm to 100 mm with increment of 10. So 20 charge radius, how it is going to scenario is 30 up to 100. How the scenario is, how this transition takes place. All things studied for both homogeneous and heterogeneous explosive models for all three, PETN, SCP, and TNT, all three. So when you do that, particularly for the prediction of mechanical properties, pressure and velocity, these things, because they can damage the structure. And there are two parameters need to be studied. One is small r, indicates the radius of the charge, and another one is capital R, the transition radius. Okay. The small r is nothing but radius of the charge. We are starting from 20, 30 up to 100. The capital R is nothing but transition radius, means near field to far field, where it's changing. That is what capital R parameter. Okay. So, and this all extracted for different time units, because we have an option in this changing 250 microsecond to 500 microsecond for different cases, and this is performed, and we can also give automatically time settings 1 into e power minus 7 to 3 into e power minus 7 using this option, and using ALE fluid quadrilateral element is employed for the present analysis, and extracted all the values of mechanical properties such as pressure variation of shock wave and velocity variation through both the mediums. And you can see here PETN of 50 mm for sample given these two for 50 mm charge radius is considered for this analysis, and you can see the pressure here and how it is going to vary, and this pressure is for how it is going to vary. And these are two different models. One is heterogeneous, other one is homogeneous. For both the things, pressure variation of PETN of 50 mm charge radius. Of course, 20 to 100 studied, for 50 shown here. Similarly, for 50 mm charge radius of PETN for second one, explosive with the homogeneous and heterogeneous model are compared for pressure variation. Now you see here, both are compared. Near field and you can see that this is homogeneous, blue color, and this red color is near field, heterogeneous. Now both the models, you can see at this point, right side they are following, they are same. Right side they are same. That means what? There is a clear indication that here is it. Up to here, left side, they are different. After crossing this point, both are same. So that is what the transition. Therefore, up to 120, let us say approximately up to 123 or something, and they behave same. So what is the transition here? 125. So if I take R equal to 125 and keep anything here, they're safe. The right side. So this is what. Similarly, for R equal to 125 distance, You can see here for homogeneous, this is for velocity is concerned, for homogeneous, heterogeneous. See, again, up to this point, they are different, and the right side, they're same. That means what? This is what transition is. So here, right side is same. So R equal to 125 for this. Similarly, pressure velocity distributions for 20 charge radius PETN, you can see here up to here there is a transition. Right side both are same and very low. And for velocity up to here there is a transition, and right side they are almost same. Or of course that is still lower than this, but they are safer. This is what near field, this is far field. So I know clearly that transition phase. Therefore, knowing this transition phase, what you can do, and knowing this region, this point. So near field, this is what the dangerous phenomenon. We should not keep anything here. Therefore, it will damage severely the unit. If I keep rather on the right side, the far field effect. So if I keep somewhere here and no damage to the system, if at all there is an effect, it is very minimal, not severe damage. So this is very, very important. Transition phase. This is also velocity transition and pressure transition. Always you need to consider both the things. You need to consider both the things. Suppose pressure is coming 50. I can't keep 50 only. Why? Because here also 50 is coming. So both are same. It is fine 50. Suppose if you get velocity, let us say 80, then you have to decide 80 only, not 50. Because you need to take care of both effects, pressure and velocity. And similarly, for PV for 100, also like this is 250, this is also 250, pressure and velocity. Therefore, if I keep beyond 250, then nothing will happen. Because it is in far field effect. And now you can see the values here, variation of the pressure here, velocity variation. And I told 20 to 100 taken total, and transition radius computed like this 50, 70, and so on, 245. For velocity variation, it's coming 60 to 250. Then there is a correlation between capital R and small r for pressure variation R equal to 2.498 small r, and velocity variation capital R equal to 2.469 small r. So these two equations using this, small r is nothing but radius of the explosive, and I can find out the transition. So I know the relation, empirical relation. So using this, you can model or you can design the real blast scenario to safeguard the equipment and the people and the surroundings. So this is what the pressure velocity relation. Similarly, same thing carried for TNT for 20. This is what 50 is coming for pressure, velocity is coming 48. And similarly, for pressure velocity distribution, it is coming 248 and 124. And this is for the TNT 100 mm. And for sample shown only 2, but connected for all these. And you can see based on that pressure variation, this is what the empirical relation R equal to 2.48 R, and for velocity R equal to 2.459 R. Using these two relations and whatever charge radius you are using for explosive, you can predict the transition distance, so that I can use this model to design and the blast scenario, so that accordingly you can keep your units wherever you want. Similarly, for SEP also it's carried out, and pressure variation are equal to 49, and velocity variation are equal to 48, and for both, and pressure and velocity distribution also for 100 it is shown, and this is what the variation, and based on these values for SEP also, when the empirical relation for pressure variation are equal to 2.475 R, for this velocity variation is R equal to 2.5 R. Then using this you can design. If you use SEP as a composition, the analysis. So this is what the final conclusion from this. So total results, total cases executed for 54 cases, and based on this, variation of transition radius computed, and this empirical relation established based on these 54 cases, and those equations based on the composition, that respective empirical relation can be used to design the systems. And this is what final for all these three together are equal to 2.490, or is coming for all three. And this is for the transition radius, charge radius, and this is for first one is pressure and second one is velocity. So this is what the final equations derived, r equal to 2.5 r. If you use this relationship, so you can satisfy safety of the equipment and personnel and surroundings. This is what the empirical relation we have derived, and for this we have used in-house developed software that's called named it as a DSS time. Okay, dynamics or shock structure interaction, and using this empirical relation, clearly we can differentiate near field and far field. If you keep the 2.5 times r, the r is transition distance. If you keep 2.5 times the radius of the explosive, then your system will be safe. That is what conclusion from the study. And also we can extend this work for in air, explosion in air you can try, and also concrete structures also can implement other materials like aluminum, steel, glass, composite materials, and structural and vibrational strength can be studied using this phenomenon. And also you can use a homogeneous explosive model also can be used for studying PU4 gamma. This can be studied for this. And this is what the some of the images. And I have shown only 1/4 model for the study. And this is what a part of the results are published in this. Are you able to see this paper? Yeah. So whatever work just presented, a part of the results are published in this. Thankful to our mentor, Dr. P. Challapandi, who is the INAE Distinguished Professor at Madras, and also our team members Saurabh Kohli and Akshay Sawant. So this is what we have published in this. This is in 2020. Okay, thank you for organizers for giving me this opportunity. And if any questions are there, I would like to answer. Because of lack of time, I could not show the implementation part because it takes more time. For executing this each case, it may take 2 hours or 3 hours to get the each case. So.
In fact, Bhaskar sir, this is really very nice topic. I have to really thank you for giving such a wonderful topic in a nutshell, because when looking at it, it was a numerical simulation of detonation, shock dynamics, and effect of pressure wave propagation underwater explosion scenarios. If you just look at it is complete hypersonics. It's all numerical simulations in complete elastic mediums and with explosives. And sir, whatever the topics which you have covered, I believe it is more like a big thesis rather than a small topic on a workshop like us. We are really honored for the topic and effort which you have taken up. and then presented it in a very nice way. I should beg a pardon, like I could not sit with your topic right from first, but the other audience, those who are there with you right from 2 o'clock, are highly blessed, because from last 1.5 hours I could not just move out from the screen, and I could see enormous amount of work, especially on gas dynamics, being done on shock propagations, particular to the penta, what we call penta is explosive, as well as trinitrotoluenes and Cimex, which is state-of-art explosives as on now. And definitely on behalf of the management, principal, faculty, students of MVSR Engineering College, we all stand up and give you a standing ovation for such a wonderful lecture, sir. Really, I should thank you for taking all your time out and giving a wonderful lecture. And this has opened doors for many of us to do research in these particular areas. And definitely we will collaborate with you in coming days and do our best. Thank you very much, Bhaskar Garu.
Thank you, sir. Thank you very much for your words, sir. And thanks for the organizers for giving me this opportunity.
Any questions from the audience can be, I think 100% this particular topic is, you will get questions on mail, sir, in coming days, where
Yes,
people
sir.
will start your research.
Yes, sir. Yes, sir. Sure, sir.
Yes. Thank you, Bhaskar Garu, for taking your time.
Yeah, thank you, sir. Thank you very much,
Thank
sir. Thank you, sir.
Thank you. Thank you, Vijay. And Vijay, I request you not to put up any feedback for this particular lecture, because Bhaskar sir does not require any feedback, what I feel like, because it was really a damn good topic. Let's try to put out into the keynote plenary lecture. This will go into the plenary lecture. Yeah. Thank you.